Last time we started discussing quantum networks, and not the quantum internet kind, but the quantum non-locality without inputs kind. And we were discussing a network where we had three parties, Alice, Bob, and Charlie. Like this. Here we have Alice, here we have Bob, here we have Charlie, and they have three sources between them. And we were trying to build some kind of intuition at what kind of output probabilities we can get out of this, because we assume that there is going to be no inputs, but we have guaranteed this kind of topology of the network that we know that Bob and Charlie share source alpha, but Alice does not know what source alpha is doing, and the same for B and beta and C and gamma. And the result of an experiment here is a probability distribution P, A, B, C, which is a probability of Alice obtaining outcome A, Bob obtaining outcome B, Charlie obtaining outcome C. Then there was the question of first we had this question can we make everybody output always the same thing? And the answer was yes, just tell everybody to output always the same thing and you'll get perfectly correlated results. So we can have a realization where the probability of 0, 0, 0 is exactly 1 because everybody just outputs always 0. Then we realize that the same thing can happen for probability 1, 1, 1 being exactly 1. Everybody is always outputting 1. It doesn't even have anything to do with these sources. They're not even communicating with each other, just outputting a constant thing. And then there was the question that we have that can we have a probability distribution in here of this form? Some of you had ideas at how to do this. So did anybody actually try? You what?
They forgot and I'm just stupid.
What did you try?
Not much, to be honest, but I just couldn't.
No, just if you want, share your thought process. What?
I thought about it for like 2 minutes.
Okay. Yeah. So then the standing question is whether we can do this or not. Now, as I said, this is usually called a triangle network because it looks like a triangle. It would be a perfect triangle if I would be able to draw straight lines. There's another network that's sometimes considered, which is the line, or for three parties, it's called the bilocality. Which is the network that you get if you put Alice here, Bob here, Charlie here, and maybe more parties, so on. And each parties share a source between each of them. This one is a little bit less studied because in this network, if you assume that you have only ABC, so Alice, Bob, and Charlie, then you can prove that in this case you must have the probability of, so probability on Alice and Charlie of AC, which is of course nothing else than sum over B of P, A, B, C. So we have this, and this actually must be of the form P, A on A times P, C on C, where again, P, A on A is just sum over B, C of P, A, B, C, and the third one you can guess yourself. Why is this the case in this network? Yes?
Because there are no links between A and C.
Exactly. If we marginalize over B, it's somehow so we sum over all possible outcomes of B, we're effectively performing a partial trace or marginalization over this thing. And what you must get is a factorized probability because they cannot even be correlated, because they don't share a common source, A and C. So in this case, we get this type of constraints, and then you can somehow see that the classical distributions you can do here must satisfy these constraints, and all of them that do can be realized in this way. So this bilocality or line, for this reason, is less interesting, or somehow I would say less studied, and most people look or work on the triangle network that are actually interested in this. So now for the rest of this lecture and next lecture, we'll be just talking about the triangle, with the caveat that most of the things that will be discussed here, or a lot of the things that we discuss here, can be generalized to arbitrary network. Because of course I can start adding parties, I can start adding then more links and so on, make it more complicated. But somehow this is the smallest non-trivial example, because this one is somehow reduced to partial triviality by this, or somehow restricted by this. This is the smallest non-trivial example. We'll be just looking at that. But most of these things can and were generalized to more general networks where you have, say, bipartite sources between some parties and you can draw a graph of where they are, or you can have multipartite sources between more parties and so on. Okay, I'm going to first of all tell you that this cannot be done neither classically nor quantumly. And I'm going to give you arguments for that a little bit later. But what that means, well, you know, we can always get P0, 0, 0 equal to 1. This is fine. P1, 1, 1 equal to 1. This is fine. But 1/2 of, so let's call this P0, P always 0, P always 1. But 1/2 of P always 0 plus P always 1. This is not fine. What this means is that the set of reachable probability distributions that we can do in a triangle network is not convex. Okay? This probably sounds at first as it's not such a big problem, but you have to realize that a lot of those things that we used in Bell inequalities and entanglement detection and steering on all of those things are based on separating functionals and hyperplane separation theorem and the convex structure of the things that you can do classically. Right? But what we have, for example, here is that we get something like this, and this is what you can do classically. This is, for example, what you can do quantumly. Of course, the quantum set is bigger than the classical, but you can say that here I have the P0, here I have the P1, and the line connecting them goes outside of the both sets, okay? So somehow it's not, these two sets that we can realize with classical and quantum are not convex. Which is somehow the whole challenge in working with this problem. Like literally most people, and this is because most people that are actually working on this, they come from Bell inequalities and the Bell theory, or a lot of them. And thus they try to use the same ideas and they just are not working here. So we need new, fresh ideas. We need people to come up with some kind of new, radical ideas. So we need you to do that. Okay, but so what does it actually mean for this PABC to be classical or be quantum? By now you should have your own intuition, or you should have your own idea at what that should mean. So how would you define that?
Can you repeat the question?
So somehow here I said that this is the set of stuff that can be done with within classical theory or with classical sources, and this is the set that can be done with quantum sources. And everybody agreed. Now, what does it mean? Like, how would you define something, or how would you model that something can be done with a classical source, and how would you define that something can be done with quantum sources? Yeah?
Classical over condition probabilities with 3 parameter hidden variables, alpha, beta, and gamma.
Okay. So PABC would be?
Sum over alpha, beta, gamma.
Okay, I'll use integrals just to make it more fancy.
And PABC given alpha, beta, gamma. PA given gamma, beta. Alpha, beta. This? Almost. Or it depends on how you define these objects. Yeah, maybe P alpha, P beta.
Exactly. Well, of course, these are just conditional probabilities. So we must have P of A, beta gamma be a positive number, sum over A of P A given beta gamma is equal to 1, and the same for all of them. P alpha is a positive number as well, or it should be a measure in principle, and the integral of this d alpha should be equal to 1. So then, if PABC of this form, we can say that it has classical realization. Because what's going on here is that the three sources, alpha, beta, and gamma, will just, according to these probabilities, generate some random number, send this number to the connected parties, and those connected parties will use these conditional probability distributions to process both of the inputs they get and output something else. Okay, here's the thing. The source, in principle, so say this force alpha, here it can maybe something like with fair probability generate 0 or 1 and send the same to Bob and Charlie. But we can also have a source that generates something like a random bit, so either 0 or 1, sends the bit to Bob, but sends the inverse to Charlie. Okay, so we can have a source, so just look at this situation. And this source alpha will, with probability 1/2, send 0 to Bob and 1 to Charlie, and with probability 1/2, 1 to Bob and 0 to Charlie. So it sends them exactly opposite stuff. Does it fall into this category or not? Why? Yep.
Can you change the condition probability to just invert its input?
Exactly. So in this case, we can say that it's sending 0 to Bob, 0 to Charlie, or 1 to Bob, 1 to Charlie, and basically do the modification on the side of Charlie. Wait, this was alpha. Yes, so do it here. Somehow include this bit flip that's happening here on Charlie into this conditional probability. So this is in fact enough. Okay, how would you define quantum realization? What should be quantum about this scenario? Yeah.
Well, the alpha, beta, and gamma should be states on some two-partite Hilbert space.
Yeah. So since we have trace and we want, since we have states and we want probability is going to be in a trace, so there's going to be rho alpha times rho beta times rho gamma. And now I'm going to say that this alpha lives on B1 and C2, the beta lives on C1 and A2 and so on. So there's going to be B1, C2, C1, A2 and A1, B2, because now you have to realize that in a quantum scenario, Alice is going to receive a state from source beta, state from source gamma, so she's going to receive two states. So she has a system A1 and A2, and she's going to have both of them. Right? Good. What's going to be the other part? Yeah?
A measurement with compounds.
But on what? Okay, so there's going to be, say, MA is going to be observable that will correspond to the output A. And what Hilbert spaces should it live on?
A1 and A2.
And why?
A is measuring this observable.
Yes, because this is the output of Alice, so it should be output of her measurement, and she can only measure the systems she receives, and that's A1 and A2. So this lives on A1 and A2, then there's something for Bob that lives on B1 and B2, and then there's something for Charlie that lives on C1 and C2. Okay? Very good. And in principle, if we would now consider infinite dimensional Hilbert spaces, we can see that what we have up here is a special, what we have up here is a special case of this. Because you can always consider these states to be just classical states diagonal in some basis, these measurements to be defined by all of that, And essentially by the same logic for why any classical correlation in Bell inequality is reachable by quantum theory, the same will hold here. So we can call this a quantum realization. There's one more thing to note. I'm abusing the notation here because this operator lives on A1, A2, but this doesn't live on A1, A2. Basically, the problem is that you put half of this state and half of this state into this P of Em and so on. So whenever you're computing this, you have to actually compute it properly, you know, like put correct things into correct things. Somehow, maybe a diagrammatic picture is here nice because you have something like row alpha here as a state. No, you have row, this is going to be A, so you have row beta here, and here you have row gamma as states in this kind of diagrammatic approach, and Alice is measuring this with MA. Okay, so she's measuring like half of this state, half of that state. And the same things are going to happen here. So all of the systems are exactly perfectly misaligned and nothing simplifies. So now there's two obvious questions to ask. Is there a probability distribution that has quantum but no classical realization? And is there a probability distribution that does not have any of those? Of course, a nice question would be to ask whether the set of classically realizable probability distribution is not empty, but that one we already know by taking the constant distributions. So this set is not empty. So now to answer the question of whether there is something that has quantum realization but not classical. This was first discovered by Tobias Fritz, something like 12 years ago, I think. And it's known as Fritz distribution. And this is interesting because it has quantum but no classical realization. And also important thing to remember here is that the construction and original proof is based on Bell inequalities. The first thing is interesting because it shows that this distinction is meaningful and we can actually do some kind of experiments here that don't have inputs but still witness properties of quantum theory. The second thing is maybe a note that the way how we are going to construct this is going to be based on Bell inequality. So there's at some point we are going to reduce the non-classicality to violation of Bell inequality, which is of course a valid thing, and still this is a very good idea, but some people were not really satisfied with this because they said like, well, this is somehow not really using the whole network, this is like repackaging Bell inequalities, maybe we should find something that's actually properly using the network stuff. And that's still an open problem, as far as I know. And also the original proof I'm going to show you is based on Bell inequalities, but also the problem with this proof is that it's not going to be entirely noise robust, but the way how to obtain the noise robust proof will be discussed next week. Okay, so here's the quantum realization. And what we're going to do is that now I'm going to put C up here for reasons that become obvious later. This is going to be the alpha source, the beta source, and this is going to be a source that's going to be distributing state psi. Now, so what's going on is that alpha and beta are classical sources. but the gamma source is the one that gives us this state psi gamma. So this is our source of quantum. This is the only quantum source that we need. Of course, you can always, if these are classical sources, you can always assume they share Bell states, and you use Bell states as perfectly correlated states. But in principle, you can also just do it with classical. Now, so what are the parties going to do? So the party C, Charlie, is just going to receive alpha and beta. So from the source alpha, he receives a random bit alpha, and from the source beta, he receives a random bit beta. Oh yeah, and these are like perfectly correlated. And alpha and beta are just random bits. So basically each source, alpha and beta, generates either 0 or 1 perfectly randomly and sends it to both of the parties. Charlie is going to receive 2 random bits and is going to output 2 random bits. Alice is going to receive beta, and she's going to receive 1/2 of this state, and she's going to output BA, where A is outcome of measuring MAX for X equals beta. So what Alice is doing is that she receives a classical input and she receives half of a state. Okay, maybe here we should say that this is just the A part of that state, or just one leg of the state. She outputs the value of beta she receives, but then she also uses the beta as a choice for measurement, because here what we are assuming is that Alice has 2 different measurements to choose from, or 2 measurement bases, and based on the random bit she receives, she measures in the basis corresponding to that bit and also outputs the output of that measurement. Okay? Is that clear? Bob does essentially the same. Bob receives a random bit and half of a quantum state, outputs the random bit, and then uses it as an input or as a choice for measurement, and outputs the output of the measurement. Now, what we can now assume is that these are 2 measurements that Alice has and 2 measurements Bob has, and this quantum state, that they violate some Bell inequalities, CHSH. And you can always, of course, find the 2 corresponding bases and the state that does this. Okay, and now if we would actually compute with what probability we obtain what outcome, we would obtain the probability distribution, which in this case looks like BA alpha B alpha beta. So these are the 2 bits outputted by A, these are the 2 bits outputted by B, these are the 2 bits outputted by C. And we can now compute this probability distribution. So far clear, right? So now if we would want to, we would know how to do this. We just need 1 source of entangled states and 2 measurements that can violate the CHSH inequality, which they have somewhere in this building lying around. They do. We just need to have 2 perfectly classical sources, but we need to have like 2 coins, which we can still find in the building. And we just need to get 3 people and start doing this type of experiment. Of course, we would need to do it fast enough so that the information cannot spread all around, but that's just like an engineering problem. Yes?
What does it mean
that the source just generates a random number. It just means that P of 0 is probability of P of 1 is equal to 1/2, and this defines this one.
Just a statement about alpha.
What?
It's just a statement about alpha.
Yes, this is telling you what the source alpha is doing.
And you wrote it down like that because you wanted to emphasize that it sends the same to both parties.
Yes, with equal probability. So now, again, I am once again abusing the notation, but this defines this probability distribution. And the same for P beta. So again, these two sources, they just toss a fair coin, get a random bit, and just send the bit to B and C and B and C and A. So just generate random bit, send it to everyone you're connected to. This guy just outputs, and these, they measure something, and based on that they output. Good. So now you know how to do this. What do you want to know more about it?
Well, we wanted to see if there's a classical realization.
Yeah, exactly. That's why we're talking about this. So now there should be a proof that there is no classical realization. So given this probability distribution, from this we can obtain the probability distribution of AB given beta alpha. Now this is a little bit confusing, but beta is the measurement choice for Alice and alpha is the measurement choice for Bob. I mean, at some point it's just not going to work out as nicely. And this is just a conditional probability because this is some probability on AB alpha beta, and from that you can get this one. Good. And now, moreover, we designed this in such a way that this probability distribution, or this one, will violate CHSH inequality, because these are just the measurement inputs of Alice and Bob, and these are their measurement outcomes. Now, what do we need to, what extra arguments do we now need to argue that must mean that these sources cannot be classical? Now, this is not a trick question, because just because you have a conditional probability violating Bell inequality doesn't mean the stuff is quantum. This can also mean that you have signaling or post-selection or many other things. So what argument do we now need to add to make sure that violation of Bell inequality by this conditional probability actually means that the source here must be quantum? Yeah?
Move the sources a bit out, and then they all send at the same time, and so that distance and light speed and so on.
Yeah, that's okay. We can assume that every line here is like 10 light years or something, or very, very, very far. So that's like that we can assume as it is. So when we were discussing loopholes in Bell inequalities, there were specifically two that we mentioned explicitly. One of them was post-selection. Do we do post-selection here? Not really. We're just computing conditional probability out of conditional probabilities out of probabilities. We're not discarding any part of our data. There's no possible outcome that could occur here that would say that we should abort the experiment and try again. So not post-selection. What was the other loophole that I mentioned? This was the signaling loophole, because I said that if Bob's measurement device would know the input of Alice, which is now beta, then this would break everything. So what we now need to argue is that this is not the case here. That actually the measurement choice for Alice, this beta, could not be known to Bob. Or to put it differently, that the value of A cannot depend on the value that Alice receives A cannot depend on value of alpha, and moreover that these two things cannot depend on gamma. That's actually the most important thing, because somehow making the argument that this beta does not depend on alpha is well, we know that they don't, because they are generated at the same time by two different sources. But to make sure that what Bob is doing does not depend on the source, on the value of gamma, because he's processing everything at the same time, then something can happen. And now here's the argument. is that first output of Bob, which is this thing, is always equal second output of C, which I want to denote no, first. But now the important thing to realize is that C does not have access to gamma, right? Which implies that the first output of C cannot depend on gamma. Yeah?
But if we have a fourth source in the center of the triangle, which determines all the others?
Yes, that's like completely underlying assumption that we don't have that.
Okay.
That's why you need to do this like fast enough. So that's why you need to do this like fast enough so that the information can spread from here and from here, but not from here to everybody else.
Wouldn't you need some sort of timing signal for all of them to align and then?
Probably.
And maybe that signal could send information too, involuntarily?
Yes, or you just synchronize the clocks and then do everything at the same time. You know, like don't talk about it, just do it at the specified times. So the first output of C cannot depend on gamma, but since that's always equal to the first output of B, from this we get that first output of B cannot depend on gamma. So the only thing that can send information between Alice and Bob somehow to tell each other or to make them correlate their measurement choices is gamma, and we now argued that the first output of Bob, which is his measurement choice, cannot depend on gamma, which means that Bob is doing independent measurements by the same logic of relating now this number and this number. You can show that the measurement choice of Alice, which is just here in this window, cannot depend on the value of gamma. So this alpha and beta are properly independent, non-correlated inputs for measurements, and the parties don't know each other's inputs. So this is a valid thing to use in the Bell inequality, and if it's violated, you know that this source cannot be classical, because that's how Bell inequalities work. Okay. So what were the two problems that we had here? The first one was that this proof is actually not robust to noise because it requires you stuff to be exactly equal to everything else, right? As long as sometimes this is not equal to that, stuff starts breaking here, because then this does not work in a Bell inequality. Okay, so the first problem was noise robustness. And this one we can actually solve, which is solved by the wagon wheel and web inequalities. So what we can do is that instead of having this type of proof, we can just find some inequality that's always satisfied by probabilities like this, but violated by some probabilities of this form, compute explicitly the probability that we are getting here and show that it violates that inequality. And the two inequalities to use here are the wagon wheel and the web inequalities. Please now note that these inequalities don't really have to be linear. Oh, actually don't have them with me. Shame. But they can be derived from using the inflation technique that I'm going to somehow try to explain during the next lecture. So this is to do for next week. The second thing that we said is not so nice is that everything here is based on the Bell inequality and two of the resources are classical, and we would want something that's like properly quantum, that where everything is classical, all of the measurements are classical and so on. So the construction here is based on Bell, and the way people try to solve this is by using the elegant joint measurement distribution. Okay, so maybe solution is the elegant joint measurement. So this is going to get shorter to EJM, so I don't have to write it ever again. Distribution. So now I will shortly explain what this is. And this is a very neat idea that, hey, maybe we can look at fully symmetric distributions. Because you see, if you have this PABC, already if A and B take values 0 and 1, there's like 8 different numbers, so we have 7 free parameters in here, because they must sum up to 1. If A, B, C take values from 1 to 4, or if they're like 2 bits, then this is 4 to the power of 3 minus 1, which is a lot. And it's very hard to work with such a big stuff. So the idea is that maybe we can take something that's very symmetric, characterized by, say, 2 or 3 parameters, and this might be easier to work with. And that's the idea here. And the first thing is that we want to be symmetric under permutation of parties. Which just means that PABC is equal to PACB is equal to PBAC, and so on. So, for example, this means that probability of observing 1, 2, 3 is the same as probability of observing 3, 2, 1 is the same as probability of observing 2, 1, 3, and so on. Right? Because what I'm doing here is that I'm always permuting the parties. And here's symmetric under joint permutations of outcomes. So the idea here is that we will have ABC live in some kind of outcome set omega, and we'll take a function phi, which is an isomorphism of omega, or permutation. Okay, so invertible transformation that just relabels the elements. And that we want to have that P ABC is equal to P phi of A, phi of B, phi of C. So, for example, for ABC taking values 1, 2, 3, 4, we must have that P111 is equal to P222 is equal to P333 is equal to P444, but also P112 is equal to P, I don't know, 443 or also P331. And probability of 1, 2, 3 is equal to probability of 4, 3, 1. I don't know. Somebody give me something random here else. Give me one more example here.
3, 1, 2.
Get it? The idea is that you can relabel all of the outcomes, but you have to relabel all of the outcomes for all of the parties. So that's why joined. Good. Why is this nice? If we enforce both of these things on a probability distribution, there's going to be three things that can happen. The first one is that A is equal to B is equal to C is equal to A. So this thing. The second thing is that A is equal to B not equal to C, or A is equal to C not equal to B, or B is equal to C not equal to A. This thing. Well, I mean, here A and B are always different, but then you can move the different one using this thing. And the third thing is that A is different from B, is different from C, is different from A. This is one of the nice things where you have to write like more non-equalities, because you have to also make like this wouldn't imply C is different from A, you know? Okay. So there's three things that can happen. Yes?
Why did you put equal to A at the end of the first one again? What for? Like
Symmetry.
because
No. That's yeah. Thanks. That was not necessary. Although not wrong.
it's not wrong definitely, but it's unnecessary.
Yes. Okay. So, but from this we can deduce that the whole PABC with like, I don't know, if A, B, and C take values from 1 to 4, then this is what? This is 4 to the power of 3, which is 64 minus 163 different numbers. This is characterized by probability of 111 and probability of 112. But it's only two numbers. But why? What about this case? Yeah?
They sum to 1.
Yeah, exactly. The last one always follows by normalization. That's why I said this would be 63, not 64. Now, of course, it's up to your liking whether you characterize it by these two numbers or you characterize it by the probability of A equal B equal to C, which is actually sum over A of probabilities A, or whatever numbers you define. It's always going to be two numbers that you will have to characterize. Which is quite nice, because now if you would be researching this and if you got some kind of nice result, you can plot pictures, because you know if you have two numbers, you can plot 2D pictures. Yes?
Why are you summing over A? You just need one A, right?
Yeah, you're summing over.
Yeah, but why are you summing? Because
So if you can also instead of characterizing by the probability of everybody outputting 1, you can say I characterize this by, I replace this number by this number, but it's the probability of everybody outputting the same thing, which is probability of everybody outputting 1 plus everybody outputting 2 plus everybody outputting 3 and so on. It's just to point out that this number is not that number.
yeah, it's n times that number.
Yes. You write everything in terms of this, some people write everything in terms of this. Don't get confused by n factors. Okay, So now to the elegant joint measurement distribution. Here, all of the sources here will be outputting the singlet state. So this is the psi minus Bell state. This is the one where you have 0, 1, minus 1, 0. And the measurements are going to be partially entangled symmetric measurements with 4 outcomes. And in this case, everything is defined analytically, so we can compute all of these probabilities analytically. And we get that we have 25 over 256 if A is equal to B is equal to C. We have 5 over 256 if A is not equal to B, not equal to C, not equal to A. And we have 1 over 256 in the last case. So in this are 3 possible cases. And if you look for the original paper by Nicolas Gison, you can actually find the states and the measurement and how to reconstruct these numbers. Which proves that this has quantum realization. Now, what's the problem with this? What do we now need to do? Come on, at least brainstorm.
Not with a bad inequality.
Yeah. So how?
Can I ask a different question?
Yes.
Can you explain what joint permutations, like symmetric and joint permutations, is the last line?
This one?
The last 2 here for, like, in the third one. Or maybe I didn't understand it. But like in the first rule, the 1 became a 4.
Yes, the 1 becomes a 4, the 2 becomes a 3, and the 3 becomes a 2.
And then in the next one, the 1 becomes a 2.
The 1 becomes a 3, the 2 becomes a 1, and the 3 becomes a 2. If you go from this. It's a different outcome permutation. It's just to stress that all of these probabilities where everybody obtains different outcome must be the same. So it's just this case. So here what I did is that 1 was renamed to 2, and I don't care what happens with the other ones. Here 1 was renamed to 3 and 1 was renamed to 4. Now here I have to do 2 renamings. I renamed 1 to 4 and 2 to 3, but this is still like an outcome permutation, must be the same. And also 1 became 3 and 2 became 1, still fine. And now I actually have to tell you what 3 of the numbers does. So 1 became 4, 2 became 3, 3 became 1. It's just, so in this step you take phi of 1 to be 4, phi of 2 to be 3, and phi of 3 to be 1. In this step, if you want to go from here to here.
I understand now. Because in the previous case, it could have been the same permutation.
Oh yeah, actually, hey, right, yeah, this is the same one. But this is completely random coincidence. At least we now practically see that people are not very good at generating random numbers. Or judging whether randoms are number. Whether numbers are random, not randoms are number. Okay, how do we now prove this is not classically realizable? What?
Inequality.
No. At least I don't know such proof.
You could assume that it does and hope to get a contradiction.
Yes. You know what the kicker is? Nobody knows how to do that. Nobody figured that out yet. People measured this in a lab, hoping it's not classically realizable. There's no proof. People tried to construct the classical realizations with machine learning models. And it seems to rule it out, but that's not a proof. That's just we tried and didn't do it, you know? It's like if I try to climb Mount Everest and fail, that doesn't mean you cannot do it. It just means I failed, you know? So people tried to construct here the classical realizations with machine learning and failed, which doesn't mean they don't exist. It just means that they didn't do it. And this is like a very big open problem, or, well, very big. It's a very big in quantum networks and this type of non-locality without inputs. If you somehow manage to solve it, I think that would be enough for a master thesis, maybe a little bit more. So, and it probably needs some fresh ideas because everybody threw everything they know at it, and the problem did not budge. The best idea that people had is that if you have fully symmetric, classically realizable network, so if you have something classical, back to the original question, what about this probability distribution where we have 0, 0, 0 and 1, 1, 1, both with equal probability 1/2. And here we have a nice finger proposition, which is the quantum finite inequality. So how would you pronounce this name? Finite. Okay. Yeah, I think so. I think he's at the University of Trier, or was in '92, and first name probably Helmut, something like that. So I would assume if PABC has quantum or classical realization, then PABC is less or equal than PA of A times PB of B times PC of C square rooted. So now, if we take P0, 0, 0 equal P1, 1, 1 equal to 1/2, then what's PA of 0? Yeah. Right? Because I just need to sum, to obtain this number, I need to sum all of the probabilities that start with 0, but that's the only non-zero of such things is this one. And to obtain this one, I need to sum all of those ones that have 0 in the middle, but that's again just this one. And here, I also need to sum all of those that have 0 at the end, but it's just this one, so everything is 1/2. So we get that 1/2 should be less or equal to 1 over 2 times square root of 2, without additional square roots. How much is this?
3 something and half of.
Yeah, it's 0.35. Because this is 1 over square root of 8, which is something like 1 over square root of 9. Or something like 1/3. 3, 5 something. So this doesn't hold. And based on thinner inequality, this proves that you cannot do this probability distribution with quantum theory. So what's the one thing remaining to do now?
Prove it.
Yeah. The first step of the proof is to realize that since we are not restricting the dimension of the quantum systems in the quantum realization, we can the sources can purify all of the states, and they can then hence send pure states, you know, because if you have a density matrix, it always has a purification by adding more systems, and the extra systems you just send to someone, send them to a random party or one of the parties always, you know, but you're going to be sending pure, based on this argument, you can say that they're going to be sending pure states. So source alpha is going to be sending psi alpha, source beta is going to be sending psi beta, the source gamma is going to be sending psi gamma. Beta L gamma. Okay, and now since we have pure states, we're going to use the one thing that we always use for pure states, which is Schmidt decomposition, right? So how would this go? So we put a number here. Like this, right? Well, not really. In the Schmidt decomposition, we know that we have positive numbers, such that their squares sum up to 1, and we have two different bases here. So this should be something like phi of L alpha, and this should be psi of L alpha, but you can always apply local unitaries to make all of the bases the same, and just put all of these local unitaries to the measurement side, okay? Alpha, beta, beta, L beta, L beta, L gamma, gamma, L gamma, L gamma, okay? And this lives on B2, C1, this lives on C2, A1, and this lives on A2, B1. Does this look at least recognizable? Okay, very good. Okay, so I'm just assuming this is the quantum realization. I argued that you can just use pure states from sources. These are the measurements on Alice, Bob, and Charlie. This is what we must have. If it has quantum realization or if it has classical realization, because we can do it with this. Okay. Now the next step, how much space do I need for this one? Is to plug in all of these things inside. So we get sum over L alpha, L beta, L gamma, L alpha prime, L beta prime, L gamma prime. You have to remember that there's like L alpha coming from here, but L alpha prime coming from the other one. Then we get lambda L alpha, lambda L alpha prime. These are on alphas. Lambda L beta prime. These are on the beta. Lambda L gamma, lambda L gamma prime, which lives on the gammas. And now the nice thing is that we can actually pick say, the A1 part of here, because that's going to be just, this thing is going to be just this, and the A2 part of this, which is going to be just that, and sandwich it, and these two things apply to this operator. Okay? Here, everything is misaligned. All of the tensor products here are misaligned with all of the tensor products here. But if you use the Schmidt decomposition, you break down everything. You break down these 3 tensor products into 6 of them, but then you can align them with that. So we go L beta, L gamma, L gamma, L alpha, L beta, MA tensor, NB tensor, OC, L beta prime, L gamma prime, L gamma prime, L alpha prime, L alpha prime, L beta prime. Good. So we just now plugged everything into everything, right? So now we isolate this part, and this part. But also, we want to, with these terms, we want to take the lambda betas and the lambda gammas, so that we get like 3 identical terms, you know? We're trying to split this huge sum into products of 3 identical terms. But we cannot take all of the lambdas here, because then there would be no lambdas left for the other term, so we just take a square root of that. You know, you have to like split everything equally among all of the terms. Also, I'll drop these alpha, beta, gamma top indices, and there the lambdas are going to be distinguished by the index on the L, which is again a little bit of abusing of notation, but it should be, you can always fill it back later. So here we go, lambda L beta, lambda L prime beta, lambda L gamma, lambda L gamma prime, square root, because we need to keep some of those for the other terms. And now we get this, L beta, L gamma, M A, L prime beta, L prime gamma, times lambda gamma, lambda L gamma prime, lambda L alpha prime, square root, L gamma, L alpha, and B, L gamma prime, L alpha prime. And the last thing, maybe let's write it a little bit conservatively here. There's going to be lambda alpha, lambda L alpha prime, lambda beta, L beta, lambda L beta prime, L alpha, L beta, OC, L alpha prime, L beta prime. Whew, okay, good. Now we have sum of product of stuff. What's the first thing that we should think about? Sum of products. Like if you see the expression like a, xa, ya, which is like if I would see these two brackets as one term and this bracket as the third term, you know, it would be essentially like that. What is that? What does it look like?
A scalar product.
Yes. And if we have a scalar product, what do we do with it? Also, we want to, you know, like we want to get an upper bound. So, yeah.
We bound it by the norm.
Yeah, exactly. Cauchy-Schwarz. So we are going to now see this as the XA and this as the YB, YA. And we get here that we get sum over some alphas. And now there's going to be a square root and there's going to be lambda L beta, lambda L prime beta, lambda L gamma, lambda L prime gamma, square rooted L beta, L gamma, MA, L prime beta, L prime gamma. And now I have to square it for the Cauchy-Schwarz to work. And here's going to be the other thing, lambda L gamma, lambda L gamma prime, lambda L alpha, lambda L alpha prime, L gamma, L alpha, and B, L gamma prime, L prime alpha squared. And this is still sum over all of the 6 indices. So that's just the norm of the first vector. And now we multiplied it by the norm of the second vector. But now we have to realize here that here we have only the indices L alpha prime, L beta prime, which means that here we are going to sum over only those indices, because when we were doing Cauchy-Schwarz up here, we should have included the L gamma and L gamma prime as an internal sum of these terms. I don't even need to know. I need this thing here. L alpha, L beta, OC, L alpha prime, L beta prime. They need to be square rooted. And here I should take a complex square.